In this video, we'll look at some further consequences of Stokes' theorem, which, remember, said that the line integral of a vector field over some closed curve is equal to the surface integral of the curl of the vector field across a surface whose boundary is that curve C. So one immediate consequence is that if you have two surfaces with the same boundary curve, then this surface integral for those two surfaces will be equal. So if you have, let's say, this surface, let's call this S1, and you compute the surface integral of the curl of f across S1, well, according to Stokes' theorem, that's just the line integral of f around C. But if another surface, let's say the one that we see here, let's call that S2, which has the same boundary C as S1, then Stokes' theorem for that surface would also apply, and it would tell us that this line integral is equal to the surface integral of the curl of f across the surface S2. So you can see that if you have two surfaces with the same boundary, then the surface integral of the curl of f will be equal for these two surfaces. So this is useful if, for example, you want to evaluate a surface integral, but the surface is too complicated, and you could choose a simpler surface with the same boundary for which the surface integral can be easily computed. You compute that easier surface integral, and you are sure, because of Stokes' theorem, that you get the answer that you were looking for. Okay, you wanted to find. So that's one application or a consequence of Stokes' theorem. Another one comes from this relation or this connection to fluids flowing. So imagine that our vector field, which, let's say, instead of F is now V, is the velocity field of some fluid, basically telling us what's the velocity vector of each point in that fluid, what the velocity vector of each point in that fluid is. Then the line integral around some curve V of V is, as we remember, it's just integrating the tangential component of V. So capital T is the unit tangent vector to the curve C. And what the meaning of this line integral is then, in that context of a fluid flowing, is that the closer V is with its direction to the tangential direction, the larger this value is. And of course, if the more it points in the opposite direction, the more negative it is. So we will get the negative value in that case. But all in all, this line integral measures the tendency of that fluid to move around C in the same direction as the orientation of C, right? Because the orientation of C will affect our unit tangent vector, and this line integral will give us a sort of measure of how much the vector field is flowing and trying to rotate that curve around as it flows. So this is why it's called, this line integral is called the circulation of V around C. Around the curve C. So this is a a different way of looking at line integrals. And in fact, let me show you two images. So, an image where we can see two closed curves sitting in the xy plane with a vector field also in the xy plane. And you can see that for this for the first curve C1, this circulation is positive, because you can see how the unit tangent vector is generally pointing in the same direction as the vectors in that vector field. So this fluid flowing would would flow in the orientation of that curve. While for the other curve C2, we can see that generally there the vectors of the vector field point in the opposite direction, right, than the orientation of the curve. So here the circulation would be negative, showing us that it has this tendency to work against the orientation of the curve. So that's one new thing, or one thing that we can use line integrals for, is to compute the circulations of vector fields around curves. This will let us actually understand curl much more intuitively than we have before. We just had the definition, but curl as this object was not, I think, properly understood until this point, the meaning of curl. And Stokes' theorem will let us understand curl a bit better as to what it does and what it represents. So let's take a surface S. Okay, so this is our surface S. Let's take a point on that surface P0, P0, and take a small disk around that point. Small disk of radius r, of radius a, let's say. So that's of radius a. Let's call that disk. Let's call that disk dA, and let's call the circle that is the boundary of the disk CA. Okay, so in that disk around that point P0, the curl of F, our vector field, is roughly the same as it is in P0. It's a good approximation to it if the disk is small enough, because F and the curl of F is continuous. So Stokes' theorem tells us that if we compute the circulation of our, well, let's use V instead of F, of our velocity field around this circle CA, which is now oriented, let's say this way. So this circulation will be equal to the surface integral of the curl of V across that disk dA. Okay, which means that we take the normal component of the curl of V and compute its surface integral across that surface dA. Now the point is, as I mentioned, that if the disk is small enough, then the curl of V over the disk is roughly the same as it is at the point P0, and also the normal vector changes continuously, so we could assume or approximate the normal vector with that normal vector at P0. So that's the normal vector at P0. If we do that, we get an approximation, and this dot product is of course then a constant, which I can just factor out of the integral, and then we have the double integral of the constant function 1 over that surface. So that's just the area of our surface, which was a disk of radius a. So this is going to be equal to the curl of v at p0 dot n at p0, the normal vector at p0, times the area of that disk, which is pi times a squared. The radius was a. So in fact, rearranging this, so this approximation, of course, is going to get better and better as a gets smaller and smaller. So when a tends to 0, then this relation will be exact. So we can rearrange this to write that the curl of v at the point p0 dotted with the normal vector at p0 is equal to, let's rearrange this, to 1 over pi times a squared, well, to, of course, the limit of that quantity as a goes to 0, quantity being 1 over pi times a squared times the line integral around that circle CA, centered at P0 and having radius A of V. So this is the circulation of V around that small circle, which gets smaller and smaller. We divide by the area of that circle, take the limit as the radius goes to 0, and this will give us the normal component of the curl at that point. So the curl, basically, we've just noticed that the curl is the measure of the rotating effect of the fluid, of this velocity field, about the axis n. So about the axis given by the normal vector n. So it is the curling effect of the vector field. That is why it's called the curl. And indeed, this curling effect is the greatest if this axis n happens to be parallel to the curl of our vector field. So that's where it's the greatest. Okay, and finally, to conclude, let us remember what we've said, that if we have a vector field f defined in R3, in the entire space, three-dimensional space R3, and it has a curl that is identically 0, then we have a conservative field. So let's prove that using Stokes' theorem. So again, prove that if we have the curl of f be identically the 0 vector, and f is defined on R3, then f is conservative. Okay, for this we just have to remember that we had a conservative vector field if its line integral along any closed curve would vanish. Okay, so take any closed curve C and compute the line integral of our vector field along that closed curve C. Well, because of Stokes' theorem, this is equal to the surface integral of the curl of f across a surface, any surface whose boundary is C, is that curve C. Okay, so all we have to do now is use the fact that the curl of f is 0. So if this is the case, then we are integrating the 0 vector across that surface, which is of course, which is going to give us just 0. So indeed, because of Stokes' theorem and because of the curl vanishing for this vector field, we see that any line integral around closed curves will give us 0, which then implies that f is conservative. Okay, so I hope you enjoyed this video, and I'll see you in the next one.